Well, hello everybody. I hope you enjoyed the talk so far. I'm happy that you're all here today, and before we start, a quick introduction about myself. Well, my name is Frederik Vogel, and I'm originally from Germany. I'm an ice engineer at the line Fukuoka, and my previous project was Create a Studio. My current one is line at. Maybe you have heard about Create a Studio. It's our latest Line family app released in last June. And you know that you can sell your own stickers via our sticker shop, right? Maybe you're even a contributor. Well, this app helps you to create your own stickers. So let me give you a quick overview. With Create a Studio, you can create your own stickers from your own images. You can manage your created stickers, and you can publish your created sticker sets all in one app. In this session, I want to talk about a specific tool you're using inside the app. I want to talk about the trimming tool. What were the conditions? How does it work? What problems we had to face, and how we achieved, in the end, our goals. By trimming, I mean to separate an object in an image from its background. The planning department showed us the planning department showed us something like here you can see in the image. They wanted to have something where you can easily trim out the image with your fingertips. And they wanted to have something smoothed, because your finger is not really, you shake a little bit if you trim it out. And it should be easy to understand. No advanced Photoshop skills are needed. Everything in one app. So let's have a look what they wanted to have in the end. So this is my attempt to try a sticker, and this is what we try to do today. We first draw the drawing path, and once the path is closed, the user should be able to mold and form the closed path, like you can see in this animation. So in the end, we have two requirements. Draw a smooth path and mold the closed one. So, first, this was one too much. Let's start with smoothing. Okay, so let's start with smoothing. This is a naive approach. We just take the points we get from the device, we combine them with a line, and, well, that's not really smooth, isn't it? Like, you can see in the upper part of the image, we have more points. In the bottom, there are less points. This is because I was drawing with different speed, and this is actually a real set I took from a device. So this doesn't bring us to the goal we want to achieve. So let's have a look at the documentation. This is actually from the, so what can we actually draw? From what elements does a path consist? So we have a move to point, we have a add a line to point, and we have something called add quad curve to point and add curve to point. So those two look very interesting. Let's have a closer look into those two path elements. So on the left side, we have our cubic Bezier curve, and on the right side, the quadratic Bezier curve. These are our two elements we can draw actually with the core graphics in iOS that the quadratic documentation gave us. So, and you can see we have control points. With the control points, we define the path. Let me show you how this looks like. So if you change the control points, you see the path is changing. So let's go a bit further. How actually does a cubic Bezier curve work? How is it constructed? How does it plot the path itself? And luckily, there's something called de Castello's algorithm. So with this one, we can draw the path. And I want to show you this in the next animation here. So this is a visualized representation of the algorithm. We interpolate between start point and control point, and between control point and end point. And we have a t that runs from 0 to 1, where 0, we are at the start point, and 1 is where we are at the end point. So let's have a look at the algorithm. Let's go through this step by step. So this is the heart of the algorithm. This basically interpolates between P1 and P2 over T, where T is, as mentioned before, between 0 and 1. All we need is a start point, control point, and T. We do this between start point and control point, and between control point and end point. This gives us the 2 points, which we interpolate again. And that gives us the final point on the curve we are looking for. So again, this time, maybe it's a bit easier to understand. So next, let's go a degree higher. Let's have a look how this algorithm works for a cubic Bezier curve. The calculation for a cubic Bezier curve is very similar to the one for the quadratic Bezier curve. Instead of 1 control point, we now have 2 control points. We need to apply the algorithm just 1 level further. Actually, if we look at start point, control point 1, and control point 2, and we want to get the first blue point on the green line, we already know how to do this. It is exactly the same as the calculation we did with the quadratic Bezier curve. So here again, the calculation works in pretty much the same way. We just have a curve of a higher degree. Instead of 3 points, we have now 4 points. We can use the quadratic Bezier function to calculate the interpolated points, which just needs 1 more step. So remember the blue line before? We do this just once for start point, control point 1, and control point 2, and once for control point 1 and control point 2 and the end point. These again gives us 2 points, which we just need to interpolate over. I think you can see a pattern here, right? We could have written this in a recursive method, but I think this way it's maybe a bit easier to see. And in the end, we interpolate between those, and we get the final point we're looking for. So now it's now we know how Bezier curves are described. But there's one more important point about the Castello's algorithm, which I want to mention here. We can split now 1 cubic Bezier curve in 2 cubic Bezier curves, actually. For example, for the first curve, just take the start point, the first green point, first blue point, and the red point as the end point. And the second part of the second curve will be the red point as a starting point, the last blue point, the last green point, and the end point as the end point. So, good, we know how to draw curves now. At least we know one, but a smooth path has more than 1 curve, right? So, well, we can just change them together. This doesn't really, something is wrong maybe. It doesn't really look smooth. Let's have a look at the control points. Control points are there, but we just added them without a real rule, right? So if we want to change cubic Bezier curves smoothly, the tangent on the point that joins curves must be the same for both curves. Points are usually starting point of the current curve and end point of the previous curve. The control point to this point must be aligned. The question is, how do we find a good position for those control points and have a smooth connection between them? Again, here's a Another algorithm that helps us, cubic Hermit interpolation. Hermit interpolation are often used way to smoothly interpolate between different points. It has its origin from a numerical analysis, splines and polynomial functions. I don't want to go too deep into it. A representation of a cubic burst can be described as you can see on the right side, starting point, control point 1, control point 2, and the end point. And luckily, there's a representation for the Hermit interpolation in the cubic Bezier world. But what is M0 and M1? Well, let me show you this in the following algorithm. This is actually an extension of the UI Bezier pass. And of course, we need to make sure our set of points has at least two members, otherwise it doesn't make much sense. This is the heart of the algorithm. To calculate one control point, we need to have 3 points. The calculated point and the first control point of the current point. We just calculate the middle point of the vector from the previous point to the next point, divided by 3, and voila, we have our m divided by 3 that we saw before. So the rest is simple. Just run over all points, make sure you have a previous point, your current point, and the next point. Calculate the control point 1, and do the same for the second control point, but this time just in reverse order, starting with the next control point. And there we have our curve. So let's have a visual representation of this algorithm to give you a better picture. P1, P2, P3, and P4 are the points on the path. The curve between P1 and P2 has already been calculated. We want to get the curve between P2 and P3. First, we want to find control point 1. So this is very easy. Just get the vector from P1 to P3, get the middle point of it, our M0, divide the vector by 3, and this is our vector, and we just need to apply this to point 2, and here we have our first control point. Now the same for the second control point. Control point 2 is part of P3, so we need a vector from P4, the next, back to P2, get the middle point of that, divide by 3 to get the vector applied to P3, and voila, we have our second control point. Well, great, and now we just can draw the curve. So let's apply our smoothing algorithm. Let's apply our algorithm to our example, sorry. So we interpolate. Oh no, yeah. So, okay, you can see here we have some side effects. It's also not really smooth, right? So let's have a look at these side effects. This is a bigger picture. So we can see we have the passes intersecting itself. We have loops, and we have sharp spikes, something we don't want to have in a smooth pass, right? The point here is, for better smoothing, you need to filter. You need to maintain an equal distance between the points. This is very important if you, if you want to have a smooth pass. Here you can see. Now it's much smoother. So let's recap here. Maintain equal distance and use a cubic Hermit interpolation to find a nice control points for a smooth connection between the single curves. So this is good. Our smoothing is working. Let's go to the next one, molding. Just a reminder, molding is changing the path. So that should be easy, right? We just need to move the points on the path and reapply our smoothing. So let's do that. That's also not really what we want. doesn't feel organic. Our points stick in this square. That's not really good. And also we have very large gaps, so that's also another problem we want to tackle. So let's first try to make it feel more organic. So let's try to add some friction. You can see here we have two squares. There's a green square and a blue square. And the points in the blue square, we apply a very low friction. So the point is almost moving with the same speed as our finger is moving, because this is right under our finger and we want to make sure that we actually can move it very well. And the points that are not in the blue square but in the green one, they have a higher friction, so they move more slowly. And this gives us a more organic feeling about it. So this is good. So let's tackle the next problem by adding additional merge points or merge points. We can prevent to have large gaps. So we introduce a minimum and a maximum distance. And by that we can, we just need to add points. Each time we move the pass, we check if this is violated, and if not, we do that. So this is good. This looks very good. So let's see the whole thing in action. So first we mark our area, and then we can kind of organically strive along the edge we want to actually trim out. And we can also scale in, new points are added. So that's good. Very well. I can start to create my own sticker set. So for the future, you saw the edges are very hard. It would be nice to have soft edges. We could take a mask of the area we want to trim out. We could apply a blur filter on it, and we can apply this mask to the actual image on the alpha value to have smooth edges. It could be applied on the whole image, or just areas. Like, for example, if you want to trim out hair, it's very difficult to find a clear line. Also, molding is still a lot of fiddling. It would be easier if it could snap to an edge. And we could do that by applying edge detection on the image itself, and then let the point snap to an edge once the edge is close enough. Also, when we scale and mold the pass, new points just pop in onto the pass and sometimes deform it a little bit. We could apply a much smoother transition by making use of the previously introduced de Castellio's algorithm and perfectly find the spot where we should add new points. This way they could appear much smoother. And I didn't talk much about the detailed implementation, but we will release, this little tool is open source under the name Clay, GitHub. I think Android just has been released yesterday. iOS will follow shortly, and feel free to play with it, improve it, or maybe even use it in your own app. So this was my little talk about the trimming feature of Creator Studio. I hope you enjoyed it. And if you have questions, I will be later there at the after show party. Feel free to ask and talk to me. Nihongo mo daijoubu desu. And well, so far, thank you very much for your time.